humanity wants to return to the moon. But the moon may not want us back. There is a place 250,000 miles from where you are sitting right now. It has no air, no warmth, no mercy. Its surface is blanketed in a fine, invisible poison that clings to everything it touches: suits, lungs, instruments, skin. Its sky offers no protection from radiation that can unravel the molecular architecture of your DNA strand by strand. And at the exact moment the sun dips below its horizon, the temperature plunges so violently, so suddenly, that metal contracts and cracks, and equipment that functioned perfectly 1 hour ago simply stops working. We call it the moon. We look up at it through bedroom windows and write poems about it. We used it to navigate oceans and mark the passage of seasons. It hangs in our sky like a familiar companion, close enough to see with the naked eye, gentle enough to cast a silver light across the grass at night. But the moon that astronauts will walk on again, the real moon, the unfiltered moon, is nothing like the one you have romanticized. It is one of the most hostile environments in the known solar system. And NASA is preparing to send human beings back to its surface for the first time in over 50 years. Not just to visit. To stay. The Artemis program is the most ambitious human spaceflight effort since Apollo. It carries with it the weight of national pride, scientific hunger, geopolitical rivalry, and genuine human courage. The astronauts who will wear those suits and plant boots on that regolith are among the most trained, most resilient human beings alive. And yet, the dangers that await them have no historical precedent. Apollo-era astronauts had no idea what they were truly walking into. The technology of that time could not measure what we now know. And what we now know should give everyone pause. If stories like this pull at something inside you, that itch of cosmic dread wrapped in scientific wonder, subscribe now. Because we are only at the surface, and it gets far darker from here. For over half a century, the moon sat largely untouched. After Apollo 17 left the lunar surface in December 1972, no human footprints were added to the dust. Robotic missions came and went. Orbiters mapped its terrain in exquisite detail. But the boot stayed home. What changed is not just technology or political will. What changed is what we found hiding in the shadows. In 2009, NASA's iCross mission crashed a spent rocket stage into the moon's south pole and watched through spectroscopic instruments as the resulting plume rose against the black. What the data revealed was startling: water ice, frozen in the permanent darkness of ancient craters that the sun has not touched in billions of years. Not traces. Meaningful quantities. Enough, potentially, to sustain a human presence, to drink, to breathe, to split into hydrogen and oxygen for rocket fuel. Suddenly the moon was not just a barren rock of symbolic value. It was a resource depot. A way station. A launch pad for something further. The Artemis program was born from this realization. Its stated goals are layered and intertwined: land the first woman and the next man on the moon, establish a long-duration lunar presence, build the Gateway orbital station, and ultimately use the moon as a stepping stone toward Mars. It is, by any measure, one of the most complex engineering endeavors in human history. But beneath the brochure language and the congressional budgets and the engineering diagrams, a quieter conversation is happening among scientists and mission planners. It is not a conversation about whether the mission is possible. It is a conversation about whether the dangers have been fully reckoned with. Because the moon we are returning to looks the same from your window. But the moon we now understand, through decades of observation and data, is a place riddled with hazards that Apollo astronauts survived largely through luck, brevity, and ignorance. And this time, we are planning to stay much longer. The first thing that will try to kill you on the moon is something you cannot see, cannot feel, and cannot easily wash away. Lunar regolith, the fine, powdery material that covers the moon's surface, looks, in photographs, almost like soft grey sand. Benign. Still. Something you might find on a beach at dusk. It is not. Because the moon has no atmosphere and no weather, its surface has never been worn down by wind or water. Every particle of lunar dust is the product of billions of years of micrometeorite impacts and intense solar radiation, and each particle retains the jagged, fractured, glass-sharp edges of the moment it was created. Under an electron microscope, lunar regolith looks less like beach sand and more like shards of broken laboratory glass. And it is electrostatically charged. The constant bombardment of solar wind particles gives the dust a persistent static charge that causes it to cling to fabric, to visors, to seals, to joints, to anything it contacts. Apollo astronauts noticed this within hours of their first moonwalks. Their suits were coated in it. The dust crept into every crevice. Harrison Schmitt, the geologist on Apollo 17, began experiencing what appeared to be allergic reactions on the lunar surface itself: sneezing, congestion, irritated airways, caused by dust particles that had found their way inside the habitat module. Those were visits measured in hours. The Artemis missions are designed for extended stays, days, weeks, potentially months for future iterations. Inhaled over time, lunar dust may be deeply dangerous. Studies on particles with similar physical properties, volcanic glass, fine silica, show that razor-edged microscopic fragments can penetrate deep into lung tissue, cause chronic inflammation, and trigger fibrosis. The Moon's dust has never been formally tested on living tissue at the exposure levels an extended mission would involve. We do not yet know the threshold. We do not yet have a reliable system to keep it entirely out. It clings. It penetrates. And it waits on every surface, every slope, every shadow. On Earth, you are protected from space by something you never think about: a magnetic field and an atmosphere working in concert, deflecting and absorbing the constant barrage of radiation that pours out from the sun and streams in from beyond the galaxy. The Moon has neither. Its magnetic field is so weak as to be nearly non-existent. Its atmosphere is so thin, a whisper trace called an exosphere, that it provides essentially zero radiation shielding. Everything that the sun emits, everything that arrives from deep space in the form of galactic cosmic rays, arrives on the lunar surface unfiltered. On a typical day, this radiation is significant but manageable with proper shielding, the same way X-rays are manageable with a lead apron. Mission planners have accounted for it. Suits have protective layers. Habitats can be reinforced. But the sun does not always behave typically. Solar particle events, massive eruptions from the sun's surface that fling charged particles across the solar system at a significant fraction of the speed of light, can arrive at the Moon with little warning. On Earth, they produce the aurora. In low Earth orbit, they trigger precautionary measures on the International Space Station. On the lunar surface, with no magnetic protection, an unshielded astronaut caught in a major solar particle event could receive a lethal radiation dose in hours. Not weeks. Not years. Hours. We have some early warning systems. Instruments orbiting the Sun, like the NOAA solar weather monitors and NASA's Solar Dynamics Observatory, give us advance notice of eruptions. In theory, this provides time to shelter. But in theory is doing enormous work in that sentence. Lead times for major events can be as short as 15 minutes. The shelter available on early Artemis surface missions will be limited. The physics of radiation shielding means any structure heavy enough to be truly protective is enormously difficult to transport from Earth. And that is just the Sun. Galactic cosmic rays, high-energy particles that originate from supernovae and other violent events elsewhere in the galaxy, arrive from every direction, constantly, and cannot be effectively deflected by any shielding material currently practical for space missions. Over time, they accumulate in human tissue, damaging DNA, increasing cancer risk, potentially causing neurological effects. Studies on mice exposed to simulated galactic cosmic ray environments show measurable cognitive decline, memory impairment, reduced decision-making capacity. The longer humans remain on the Moon, the higher the cumulative exposure. The universe is radiating its indifference directly into human biology, and there is no fully satisfying engineering solution yet in existence. The Moon rotates slowly, so slowly that a single lunar day lasts approximately 29 Earth days. This means the sunlit side of the Moon bakes under continuous solar exposure for 2 weeks at a time. Surface temperatures in direct sunlight can reach over 120 degrees Celsius. Hot enough to boil water. Then night falls. And the temperature drops to minus 170 degrees Celsius. Sometimes colder. This is not a temperature swing. It is a thermal apocalypse. In the span of hours, the same patch of ground transitions from searing heat to cold so profound it approaches the theoretical lower limits of what materials can endure. Metal that expanded in the heat contracts violently. Seals that held under pressure in the sunlight may fail in the dark. Equipment calibrated for one temperature range finds itself in another entirely. Apollo missions were carefully timed to operate during lunar morning, when temperatures were rising but not yet extreme, and before the long lunar night arrived. Early Artemis surface missions will follow similar logic. But the longer duration missions planned for later in the decade cannot dodge the lunar night indefinitely. Engineers are designing systems to handle these extremes. But history is littered with the wreckage of systems that performed flawlessly in testing and failed in the specific, unforgiving conditions of space. The Mars Climate Orbiter was lost because one engineering team used metric units and another used imperial. Challenger was lost because an O-ring was not rated for cold launch temperatures that were present on the morning of January 28, 1986. The details of material behavior at extreme temperatures are not abstractions. They are the difference between a mission and a memorial. And beneath the thermal extremes lies an additional threat: moonquakes. The moon is not geologically dead. It contracts as it cools, generating seismic events that can persist for hours, sometimes 10 times longer than a comparable earthquake on Earth, because the dry, rigid lunar rock has no water or soft sediment to absorb the vibrations. Future lunar habitats will be built on a surface that shakes, fractures, and shifts in ways that Earth-based structural engineering has no direct analog for. Imagine building a home on a surface that can suddenly begin trembling, and keep trembling for an hour, at 240,000 miles from the nearest hospital. There is a physical barrier between the Moon and Earth that no amount of technology has yet dissolved: the communication delay. At the Moon's average distance, a signal traveling at the speed of light takes about 1.3 seconds to arrive. Round trip, that is 2.6 seconds of lag. For voice communication and data transmission, this is manageable, different from a real-time conversation, but workable. But what it represents psychologically is something harder to engineer around. Every message home takes over a second to arrive. Every reply takes the same time back. Mission control, which guided Apollo astronauts through every critical decision in near real time, will always be slightly behind. For the fast, explosive decision-making that a crisis demands, the Moon is already, even at its closest, a long way from any help. And help cannot come quickly. A rescue mission to the Moon, in any current or near-future operational framework, is not a matter of hours. It is a matter of days or weeks of preparation at minimum. If an astronaut is injured, if a system fails catastrophically, if the pressurized habitat is breached, the crew is, fundamentally, on their own. They must solve the problem with what they carried, using knowledge they brought, in a suit that was not designed for the scenario unfolding. Apollo 13 demonstrated what human ingenuity and mission control collaboration can achieve under crisis. But Apollo 13 happened in transit, in a spacecraft, not on the surface of the Moon during a moonquake, in a habitat losing pressure, with a dust storm compromising solar panel efficiency. The psychological literature on long-duration spaceflight isolation is sobering. Research from Antarctic winter-over stations, where small crews are isolated for months in extreme conditions, documents cognitive decline, interpersonal conflict, sleep disruption, and what researchers call third-quarter phenomenon, a measurable dip in morale and performance around the three-quarter mark of an isolated mission. Scale that to the Moon, add radiation anxiety, add suit anxiety, add the dust that never fully goes away, and the question of human psychological endurance becomes as technically challenging as the question of rocket fuel. In 2023, NASA's Lunar Reconnaissance Orbiter captured high-resolution imagery of the Moon's south polar region, the target of the Artemis landing sites, and revealed something that complicated the mission profile in ways engineers are still working through. The terrain around the lunar South Pole is ancient beyond comprehension. Some of it has not been touched by direct sunlight in over 3 billion years. The permanently shadowed craters that hold the water ice are extraordinarily cold, colder than the surface of Pluto, and the ice is not sitting on top of the surface in convenient sheets. It is locked within the regolith itself, mixed with dust and other volatile compounds, some of which are toxic. The extraction of that water, the resource that makes long-duration lunar presence theoretically possible, is not a simple matter of scooping material off the ground. It is a mining operation conducted by astronauts in bulky pressure suits, in darkness, at extreme cold, extracting material that is chemically complex and mechanically difficult to work with. The permanently shadowed regions also cannot use solar power. Every piece of equipment that ventures into them, every robotic prospector, every drilling apparatus, must carry its own power source or be connected by cable to a sunlit energy supply. This is solvable. But it adds layers of complexity, failure points, and mission risk that did not exist in Apollo's relatively simple geology. And there is something else. The lunar South Pole sits at the edge of a massive ancient impact basin, the South Pole Basin Basin, one of the largest impact craters in the solar system, roughly 2,500 kilometers across and 8 kilometers deep. The geology of the region is dramatically different from the flat equatorial plains where Apollo landed. It is rugged. It is shadowed. It is beautiful in imagery and extraordinarily difficult to navigate in reality. We have mapped it from orbit. We have analyzed it remotely. But no human being has ever stood there, looked down into those frozen craters, and felt the specific gravity of what we are asking people to do. Here is the harder truth, and it lives beneath all the warnings. We go because the alternative is to stop. The moon is not simply a scientific target anymore. It sits at the center of a geopolitical contest that would have been familiar to the analysts of 1969 but has now expanded to include new players, new stakes, and new timelines. China's Chang'e program has landed on the lunar far side. Its U-2 rovers have operated on the lunar surface. The China National Space Administration has announced ambitions for a crewed moon landing before the end of this decade and a permanent lunar research station by 2035. The resources of the moon, the water ice, the helium-3 embedded in the regolith by decades of solar wind, the sheer strategic value of orbital infrastructure above it, are not hypothetical prizes. They are the rationale behind a quiet but unmistakable space race that is already underway. If the United States and its international partners cede the lunar South Pole, the site of the water ice, the resource that makes everything else possible, the consequences extend far beyond science. They extend into the long-term calculus of who controls the infrastructure of deep space access. And beyond the geopolitics, beyond even the resource economics, there is the deeper logic that has driven human exploration since before written history. We go because not going is a kind of death. A slow, comfortable, civilizational death, the death of a species that looked at the stars and turned away. The Artemis astronauts know the risks better than anyone. They have read the radiation studies. They have trained in the suits. They understand the dust problem and the thermal problem and the isolation problem and the moonquake problem. They volunteered anyway. There is something in that, in the specific kind of courage required to board a rocket knowing the universe will not soften its edges for you, that resists clinical analysis. It is not recklessness. It is not ignorance. It is a very particular human insistence that the next horizon is worth the cost of reaching it. But here is what the mission briefings do not fully capture, what the press releases smooth over, what the engineering reviews will confront in their own quiet language as the missions approach. We are returning to the moon with knowledge that the Apollo astronauts did not have, but we are also returning with gaps that no amount of pre-mission analysis can fully close. The moon's surface was visited by 12 people, across 6 missions, for a combined total of approximately 80 hours of EVA time. 80 hours of human experience on an entire world. The equivalent of one long weekend, distributed across a dozen people. We do not know how the human cardiovascular system will respond to extended low-gravity exposure at 1/6 of Earth's pull, not the months of data we have from zero gravity in orbit, but the specific, sustained, partial gravity of the lunar surface. We do not know the precise long-term pulmonary response to repeated lunar dust exposure. We do not know how the moon's radiation environment interacts with the specific behavioral and neurological profile of humans under sustained mission stress. We know enough to be cautious. We do not know enough to be certain. Some of what we will learn the hard way. That is not a criticism. It is the definition of exploration. Columbus did not know the Atlantic. Amundsen did not know the interior of Antarctica. The test pilots of the early jet age did not know where the edges of the envelope were until they flew past them. Some of them did not return. The question is not whether Artemis will encounter dangers that were not fully anticipated. It will. The question is whether the margin of safety is wide enough to survive the surprises, whether the contingencies are robust enough to handle the unknowns, whether the human beings who will stand on that grey, silent, hostile surface will have everything they need when the thing that was not in the mission plan occurs. History suggests that these questions cannot be answered in advance. They can only be answered by going. Stand outside on a clear night and look up, there it is. Pale and still, hanging in the dark with a patience that predates humanity by billions of years. It was there when the first cells replicated in Earth's primordial oceans. It was there when the first mammals looked up from the forest floor. It has watched every war, every harvest, every birth. It does not care that we are coming back. It never cared the first time. In a few years, if everything goes according to the carefully laid plans of thousands of engineers, scientists, and mission specialists, and also if the sun behaves itself, and the dust doesn't destroy the suits, and the moonquakes don't crack the habitat seals, and the radiation doesn't cross the line, and the human minds at the end of those 1.3-second communication delays hold together under pressure we cannot fully simulate, Human footprints will return to that ancient surface. They will be different footprints, made by different people, pointing toward different destinations. But they will carry the same weight as the ones that came before, the strange, stubborn, irreducible human conviction that going is better than staying, that knowing is better than imagining, that the darkness is worth entering if there is something on the other side. The moon will not become safer because we decide to return to it. Its dust will remain sharp. Its radiation will remain relentless. Its night will remain absolute. Its silence will remain exactly what it has always been, total, ancient, and indifferent. We go anyway. We always have. And somewhere out past the moon, past Mars, past the outer planets spinning in their cold distant orbits, there are more worlds waiting, each one more indifferent, more extreme, more silent than the last. The universe does not hate us. It simply does not care. And we keep going.